Hello everyone, my name is Papadopoulos, and together Emily Kempfer and I will tell you about the new features that have been implemented in ORCA using automated code generation for correlation methods. Now, you might be wondering why you would want to use code generation to develop wave-functional correlation methods. It's because the development of those theories have reached a significant level of complexity, making manual implementation oftentimes unfeasible. Imagine having to implement thousands of equations and making a single mistake immediately invalidating the implementation of your new theory. Now, this is quite undesirable, but luckily for us, the derivation of the equations of correlation methods is rather systematic, and one thing that a computer excels at is systematic work. So why not let the computer generate the equations for us and even have it generate the code for us as well? This way, we can remove the human error by not having to worry about making mistakes in our implementation, and even reducing development time because we don't have to implement thousands of equations. This frees up the time of the developer so they can spend time on the most important part of developing a theory, which is arguably developing the theory itself. Now, how do we end up with our generated code? Here I've shown you a high-level overview of ORCA's automated generator environment, also known as the AGE. The starting point is the Ansatz. So for coupled cluster, this would be your T operator or your excitation operators. But just having the Ansatz is not enough. The equation generator also needs to know what type of equation you want to generate. For instance, the coupled cluster residual equations. And ideally, you formulate these equations in a general way. This makes it so they are valid for arbitrary level of coupled cluster or any other correlation method, and making it so that the infrastructure is valid for these higher level of correlation methods as well. All right, so now combining the Ansatz and the type of equation, we can have the equation generator generate the equations, and by factorizing those equations, we end up with our final working equations that have the correct scaling behavior. Now, we can take these working equations as a simple text file, and we can give that to the code generator. And this will generate the ORCA source code for us, which is then integrated into the AUTOCI module of ORCA, which is where the generated code resides. All right, so let's have a look at the new features, starting off with the first order properties. As you can see in this table, we have implemented energies and analytic nuclear gradients for a variety of methods, ranging from CI to coupled cluster, most notably CCSD(T), and even Muller-Placid perturbation theory for both RHF and UHF. We even have energies for other flavors of CI and coupled cluster, as shown here. We even have spin-adapted versions of CISDT and CCSDT. Moving on to second order properties, you can now calculate the polarizability at the UHF CCSD level of theory with an unrelaxed density. You could even, in AUTOCI, calculate the polarizability with MP2 with a relaxed density, and even the NMR shielding tensors. All right, so that's about the new features. Let's go a little bit more into detail about each feature. As I've mentioned, we've added a range of nuclear gradients for CI, coupled cluster, and Muller-Placid perturbation theory. I won't discuss the theory here, but if you're interested, you can have a look at our latest AGE article in which all the theory is laid out. Okay, but what are these nuclear gradients actually good for? Well, besides, they enable first order properties, among them geometry optimizations. So now you can optimize your geometries with these highly accurate methods with analytic gradients, so you don't have to rely on slower numerical gradients. And using them is quite easy as well. I've shown you an example of a CCSD geometry optimization here. The only thing that's required really is you specify your method, so AutoCI dash and then your correlation method, in combination with an optimization keyword such as opt. Now, if you want to use another method, not CCSD, simply swap out CCSD for any other method of your choice. Alright, but I'm sure you're curious as to how applicable these methods are to your research and what you can expect from them in terms of performance. So to that end, we will show you benchmark results of several methods, starting off with CCSD. And you can find all the relevant benchmark settings over here in the bottom left corner. Now, here, starting off with RHF CCSD, we've plotted the number of basis functions against the time it takes to do a single gradient or optimization step on linear alkenes of increasing size. Now, as can be seen in the figure, we can reach 400 basis functions, which corresponds to nonene, so an alkene with 9 carbons, quite easily in about a day. And going larger means the calculation time increases, and nearing 600 basis functions means the calculation takes roughly a week. Now, but the generated code is parallelized, so we can use more processes to reduce the computational time. Here we have tetradecene, which corresponds to about 600 basis functions. We can do a gradient calculation on that with 4 processes in about 80 hours. And by using 8 processes, we can reduce that time further to about 2 days. So realistically, you could do a geometry optimization on a system the size of tetradecene with these settings in about 2 weeks or so. Now, shifting to the right, we have UHF CCSD. Now, this is a more expensive method than RHF CCSD, so we cannot reach the same number of basis functions in the same amount of time. Here we went up until decene, which in serial takes about 120 hours or 5 days to calculate the gradient for, but if we use 8 processes, this is reduced to about 1 day. So here you could do, for UHF CCSD, you could do geometry optimization with these settings for systems the size of decene. Okay. Moving on to the gold standard, CCSD parenthesis T. This is a more expensive method than CCSD due to the explicit triples contributions, so, which makes it scales as n to the 7th as opposed to CCSD's n to the 6th. And this is immediately obvious from the figures. So starting on the left, we can see that if we go up until about 300 basis functions, so this corresponds to octene or 8 carbons. This already takes nearly a week in serial, and if you use 4 processes, this takes about 2 days. So realistically, this is probably the size, the system size that you can target. Similarly, with UHF CCSD, it's much more expensive, so we cannot reach as far. But we can reach about 250-ish basis functions within a day. So you could do geometry optimizations of systems the size of hexene in this case, probably also within 2 weeks. Now, the final gradient that I want to discuss with you is the MP gradients. And the reason for that is because these gradients, and specifically here MP4SDQ and MP4SDTQ, or just MP4, have scale the same as CCSD and CCSD parenthesis T respectively, but they have the benefit of not having to go through an iterative procedure to determine the amplitudes. So here, starting off with RHF MP4SDQ, which scales the same as CCSD, as I've said, we can see that we can easily reach 250 basis functions within an hour. So you could do a geometry optimization on systems of these sizes in a day. And yeah, so shifting over to the right, where we have MP4SDTQ or MP4, this is notably more expensive. Reaching the same system size takes about an order of magnitude longer to calculate, but still, for systems this size, it only takes about a day to perform a single gradient step. So you can still do geometry optimizations on systems these sizes quite comfortably. All right, I think that's enough gradient talk. So let's move over to the final gradient, or the final comparison between generated code and handwritten code, because it's quite important to know how well we do against handwritten code that's been optimized over years. So here we've compared the average iteration timings of the AUTOCI module, which uses generated code, and of the handwritten code, which is implemented in the MCI module of ORCA. And as you can see, is that for these methods, or the generated code rather, performs equally as well as the handwritten code, or in the case of UHF CCSD, it performs equally as well. Now, this goes to show that code generation is a viable tool that is able to deliver well-performing code and will be able to take us into the future of the development of wave function-based methods. Now, with that, I will hand over the word to Emily.
Hi everyone, my name is Emily Kempfer, and as Stan mentioned earlier, we have a lot of new features within the ORCA AUTOCI framework, including second-order properties. So here I'm showing the new properties that are available using AUTOCI, the CCSD analytic polarizability and analytic gradient, and the MP2 analytic polarizability and NMR shielding. The keywords needed for calling these properties are the same as for any other method. However, we call the AUTOCI keyword for the method you want to perform, whether it be AUTOCI CCSD or AUTOCI MP2. I do want to point out that for MP2 methodologies, we can only use the relaxed density. So you do have to specify in the AUTOCI block density relaxed. Now, as shown before, we do perform benchmarking on some properties. So here we show the closed shell UHF CCSD analytic polarizability with 1, 4, and 8 processes. We see, as shown before, they all scale the same, but using more processes results in a shorter time. And because these are second-order properties, we cannot go as far with the number of basis functions as the first-order properties. So here we do show that our max number of basis functions is about 250. And this is mostly due to the computational cost of the second-order properties. However, we can still take relatively decently large-sized systems. Now, we can also examine some estimated size limits. So with this, we can directly compare RHF and UHF methodologies, and we see that we consistently demonstrate that RHF can handle slightly larger molecules, or more basis functions, due to the equal treatment of electrons, and this is shown with any other methodology out there. Now, we also show that the response theories can examine molecules with about 350 and 600 for CCSD and MP2 respectively, which is again less than that of our first-order properties, which is again due to the fact that second-order properties are computationally more expensive. Now we can also look at how AUTOCI can be used in action. So here we do a geometry optimization of an allyl radical using this tight opt keyword at the CCSD parentheses T def2 TZVP level of theory using the appropriate AUTOCI keyword. So we also calculate the hyperfine coupling constants here as well for all hydrogens by requesting the property in the EPR NMR block as well. So with this calculation, we first look at the geometry optimization. We see that with this molecule, we demonstrate a very consistent or a very typical geometry optimization using this AUTOCI level of theory. Now, we can also further look at the results and look at the hyperfine coupling constants that we get out. We can look at the alpha, beta, and gamma results and compare them directly to experiment. And we see that our results are within about 3 megahertz to the experimental values. Now, with this, we can say that we can get chemically relevant hyperfine coupling values. Now, moving forward, code generation will be crucial for developing future code and methods due to increasing complexity. Now, to keep introducing new methods and extensions to current methods, using a generated code base is really necessary for saving time and increasing efficiency. Now, our code generation allows for viable production of complex code for increased multi-reference levels, higher order perturbation, higher order excitation levels for coupled cluster and CI methodologies, and also implementing analytic derivatives of wave function theories. Now, code generation is tightly integrated into ORCA. And what that means is that with any optimization in the generated code, we can easily propagate it into the entire code base and thus into the ORCA software. So for example, say there comes a faster, more efficient way of handling double excitations. We can implement this new, more efficient method and update concurrently within every methodology which uses double excitations for the AUTOCI framework, allowing ease of updating or correcting current AUTOCI methodologies. Now, I want to thank you so much for your time, and we look forward to seeing the interesting research that'll be done using the new AUTOCI methodologies in ORCA 6.